After skimming past the sun at a distance that would have shredded an ordinary comet, 3I/Atlas was expected to fade into the familiar patterns astronomers knew. It did not. On November 30th, 2025, the Hubble Space Telescope pivoted back toward the object long after the critical perihelion had passed. What it recorded was far from a simple dispersing tail. Instead, a vast, luminous structure, shaped like a teardrop, hovered around the core of 3I/Atlas. Even more striking was its orientation. The narrow tip of this glowing formation pointed directly at the sun, forming what scientists identify as an anti-tail, a rare feature that contradicts everyday intuition. This behavior echoed warnings previously raised by Avi Loeb, whose forecasts about 3I/Atlas had already sparked debate. While some researchers saw confirmation of his predictions, others advised caution. NASA maintained that conventional cometary physics could still account for Hubble's observations, pending more spectral analysis. The mystery remained. If 3I/Atlas is a standard comet, why does it continue exhibiting behavior that appears entirely atypical? By the close of 2025, one fact was no longer in dispute. 3I/Atlas's trajectory through space had revealed its true nature. It was on a hyperbolic path, unbound to the sun, and never part of the solar system. Music, like Oumuamua in 2017 and 2I/Borisov in 2019, 3I/Atlas was a visitor passing through our cosmic neighborhood. That classification alone placed it among an extraordinarily rare category. Only 2 interstellar objects have been confirmed previously, each challenging expectations in unique ways. Oumuamua lacked a clear cometary tail, while Borisov acted more like a typical comet but contained chemical signatures unlike anything observed before. Adding 3I/Atlas to that exclusive list reminded astronomers that they were confronting an object without precedent. As it neared perihelion, the closest point to the sun, expectations remained cautious. Comets are inherently fragile. Close solar encounters can crack surfaces, trigger violent jets, or disperse loosely bound material, often leaving chaotic, difficult-to-interpret remnants. If 3I/Atlas followed this familiar pattern, its aftermath would be noisy, unstable, and frustrating for researchers. Yet, nothing of the sort occurred. After perihelion, the object did not collapse into disorder. Instead, it retained coherence sufficient for detailed observation. On November 30th, 2025, Hubble observed 3I/Atlas at roughly 178 million miles from Earth, far enough that atmospheric distortion was irrelevant. The view was clean, direct, and free from the uncertainties inherent to ground-based imaging, making the data exceptionally valuable. Post-perihelion images of interstellar objects are extraordinarily rare, particularly when the body survives intact. Scientists were no longer speculating about the effects of solar stress. They were seeing the results. From a research standpoint, this should have been a quiet period. The most dangerous phase had passed. The sun's influence was waning, and in theory, the object should have become stable and predictable. Yet, stability did not equate to simplicity. At the exact moment when clarity was anticipated, Hubble revealed an anomaly that defied expectations, marking a far more unsettling chapter in the story of 3I/Atlas. Examining the post-perihelion image, one feature dominated immediately. Encircling the core was a vast, luminous region, smooth and uninterrupted, forming an unmistakable teardrop suspended in space. A bright, rounded area near the center extended into a narrow, tapering tip. The formation was organized, deliberate in appearance, unlike the scattered, wispy tails typical of comets. Measurements from Hubble indicated the rounded region spanned roughly 25,000 miles, with the narrowing extension stretching nearly 37,000 miles. These were prominent, defining features, not subtle artifacts. Conventional comet tails are thin, uneven, shaped by solar wind and radiation pressure, often fanning outward and losing coherence with distance. The structure around 3I/Atlas, in contrast, was sharply defined, bright, and directional. It was not a dispersing cloud. It was a cohesive form. This distinction redefined interpretation. A loose tail can be dismissed as debris reacting to sunlight, but a compact, directional structure demands attention. It implied that the glow was produced in a controlled, consistent manner, even after perihelion. For many observers, this raised a red flag. Perihelion typically damages fragile comets, with heat fracturing surfaces and triggering erratic jets. Yet 3I/Atlas displayed a stable, intact structure. The teardrop persisted, forcing scientists to reconsider easy explanations. If solar heating created it, why was it so clean afterward? If leftover material, why hadn't it dispersed or faded? These questions struck at the heart of the mystery. How could a structure this large and defined endure a solar encounter that should have destroyed it? Further intrigue came from its directionality. Normally, a comet's tail points away from the sun, pushed by sunlight and solar wind. Rarely, an anti-tail can appear to point sunward, but such occurrences are faint, brief, or angle-dependent. In 3I/Atlas, the anti-tail was bright, well-defined, and stretched tens of thousands of miles, forming the tip of the luminous teardrop itself. Visually, the effect was disconcerting. The sharp end pointed toward the sun, seemingly resisting solar forces. It aligned perfectly with the rounded luminous region, suggesting a single, coherent system rather than a separate or illusory feature. Typically, anti-tails are geometric illusions, fleeting and dependent on perspective. Here, the structure remained fixed, persistent, and sharply defined, defying casual explanations. Its stability challenged assumptions. If the effect were purely geometric, it should have faded or distorted with changing conditions. Yet it held firm, even after the solar encounter. Questions mounted. If the anti-tail was geometric, why was it so organized and stable? If not, what maintained it? Even more puzzling, post-perihelion images showed little change compared to July 2025. The teardrop and its extension retained their orientation and scale, implying minimal reaction to solar stress. Perihelion is the harshest phase for a comet. Solar radiation peaks, surfaces fracture, internal stress rises, and loosely bound material typically disperses or shifts. Some comets do not survive at all. Yet 3I/Atlas emerged nearly unchanged, its glowing structure intact and coherent. Typical post-perihelion evolution, tails thinning, emission patterns shifting, bright regions fading, was largely absent. Extreme heating should have caused visible change. The lack thereof implied that the mechanism shaping the glow persisted before and after perihelion. No definitive conclusions could yet be drawn, but assumptions were quietly reconsidered. For an interstellar object to withstand such extremes and remain largely unaltered, the question shifted. Not how did it survive, but why did it not change? Avi Loeb offered an alternative interpretation, focusing not on categorization, but on physical formation and stability. He suggested the teardrop might consist of large solid fragments separating from the main body. Heavier and cohesive, these fragments would resist rapid dispersal, and uneven gas escape could produce subtle, measurable non-gravitational acceleration, shifting the path slightly without external forces. Non-gravitational acceleration is common in comets, linked to outgassing as ice vaporizes. Loeb's insight was that the resulting structure appeared coherent, directional, and persistent. Crucially, he predicted the anti-tail's location, which closely matched the Hubble observations, supporting his model. Many cautioned that a single geometric alignment does not validate a full model, and coincidence cannot be excluded without further data. Loeb presented a hypothesis based on observable behavior, not definitive proof. The image raised questions warranting deeper examination, contingent on future measurements of composition and dynamics. NASA, meanwhile, remained measured. Current observations required no new object category or unconventional mechanism. 3I/Atlas's motion, including subtle non-gravitational effects, could be explained by standard cometary physics. Non-gravitational acceleration through uneven outgassing is well documented. From this perspective, what appears unusual need not imply the unknown. Outgassing, radiation pressure, solar wind, and orbital geometry can produce complex, seemingly organized structures. Hubble images alone reveal form, not substance. Composition and emission mechanisms remain uncertain without spectral data. Extraordinary interpretations demand extraordinary evidence. Until multiple, independent measurements confirm anomalies, NASA maintains a provisional stance. Behavior may prove unusual, but unusual does not equal inexplicable. The debate revolves around thresholds. How much evidence justifies moving beyond established models? With imaging reaching its limits, attention turned to spectral evidence. Hubble is conducting ultraviolet spectroscopy to decompose 3I/Atlas's glow into specific wavelengths. Unlike images, spectroscopy identifies the actual emitting material. The aim is to detect familiar cometary gases, carbon monoxide, carbon dioxide, water vapor, released as ice's heat. Identifying these would anchor interpretation, showing that the striking teardrop is driven by no materials. Conversely, if expected gases are weak, absent, or inconsistent with brightness and structure, scientists must reconsider the source. Spectroscopy defines boundaries, confirming what cannot produce the observed glow. Until those results arrive, explanations remain provisional. 3I/Atlas may be an interstellar comet with unusual geometry or reveal gaps in current models. Either outcome, spectroscopy is the first step toward resolution. For now, the mystery balances between familiar physics and questions extending beyond form and motion. If expected cometary signatures are absent, what alternative explanation emerges? By the end of this observation window, several facts are clear. 3I/Atlas survived perihelion intact, retaining a stable teardrop structure and anti-tail pointing sunward, features rarely seen in interstellar objects. Interpretation remains unresolved. Some researchers see the image as a call to refine assumptions about cometary fragility, mass distribution, fragmentation, and forces shaping non-solar system material. Others maintain caution. Unusual is not inexplicable, and non-gravitational outgassing is well understood. The image is striking but inconclusive. Without knowing the composition generating the glow, morphology alone cannot justify conclusions. The story continues as Hubble moves beyond imaging into ultraviolet spectroscopy to determine whether 3I/Atlas emits familiar gases or exhibits behavior beyond existing models. The ultraviolet observations were designed to go beyond what eyes could see. While images reveal form, spectral data can expose the invisible fingerprints of matter, tracing the composition, density, and dynamics of material around 3I/Atlas. This distinction is critical. A cometary tail might look impressive, but its appearance could be misleading. Only by analyzing the wavelengths of emitted light could scientists determine whether the glow corresponded to familiar cometary chemistry or hinted at something truly unexpected. Early ultraviolet readings were tantalizing yet inconclusive. Preliminary scans indicated faint traces of common molecules, but the intensity and distribution of light did not align neatly with any conventional model. Some wavelengths were stronger than anticipated, others weaker. The data suggested that, while 3I/Atlas might share some characteristics with solar system comets, there was a persistent anomaly, one that resisted easy categorization. Scientists were forced to confront a deeper question. If the teardrop structure and anti-tail could not be fully explained by standard comet physics, what alternative mechanisms might be at work? The answer required looking at the physics of cohesion, outgassing, and even rotational dynamics. In some models, large solid fragments within the comet could produce a more coherent luminous formation. Spinning fragments could create a stable, directional glow while still interacting with solar radiation in ways that mimic familiar tail structures. This concept offered a bridge between observation and explanation, but remained speculative until confirmed by further data. Rotation itself might play a subtle but crucial role. A comet spinning along an axis aligned with its trajectory could funnel material into preferential directions, shaping the teardrop's tip and reinforcing the anti-tail's alignment. In theory, even small variations in angular momentum could produce highly organized features. Combined with the uneven outgassing of volatile ices, this dynamic system could maintain structural integrity longer than previously expected. Yet despite these plausible mechanisms, the persistence of the shape remained